Okay, to further study kinetics, we have to look at mechanisms. What a mechanism is that often chemical reactions take place in a series of steps. So one chemical reaction will take place, and then those products might combine or might react with another reactant, and so forth. And then there might be a third reaction, and collectively, all of those would combine to make the chemical reaction we think that is occurring. But actually, what really occurs is that there is a mechanism of a number of chemical reactions. And one of those chemical reactions always is going to be slower than the other ones. And whichever one is the slowest of the steps determines how fast the reaction can take place. And we're going to call those steps elementary reactions. And so this is unit 5.4, but very much related to it is 5.7. So it looks like we're going to be skipping some spots here, but we're not really going to be skipping spots. Okay, so definition of rate mechanism. So a series of simpler reactions that ultimately give us the chemical reaction that we think is taking place. And a couple things to kind of keep in mind is that if you add up all of the elementary steps with the reactants and products, it gives you the overall balanced chemical equation. And we've talked about those balanced chemical equations many times in earlier sections, in earlier units also. And then one of those elementary steps will be the slowest step. And that slowest step is going to determine how fast the reaction can take place. And the rate determining step should predict the same rate law as determined experimentally. So all those ways that we figured out rate law previously should match up with what we determine in this section here. So a couple more vocabularies. Reactions take place by either a reactant decomposing or multiple reactants colliding with each other with the correct orientation and the correct amount of energy for the reaction to take place. And these could be bimolecular. They would involve two reactants. Okay, and these could be, by the way, elementary steps, or they could also be overall. But you could have, in this case, A plus B, or you could have A plus A. Unimolecular, this would be a decomposition style reaction. And then we have termolecular, and these would require you to have three items all simultaneously collide perfectly with the right orientation and enough energy for that reaction to take place. Very unlikely for three or more atoms, molecules, whatever, to collide perfectly for the reaction to take place. So the more likely ones would be unimolecular and bimolecular. But of course, I do have these elementary steps. It could be three A's coming together. But again, very unlikely. It could be, in this case, two A's and a B. It could be, any combination of these, an A and two B's, three different chemicals. So we've mentioned the rate determining step before, and that's going to be the slowest of these elementary steps. So think about if you had three individuals that are all tied together and you were told to run from point A to point B, you guys could only move as fast as the slowest person. So think of it that way. A couple more vocabularies is intermediates, and we'll get to catalysts. So intermediates would be items that you might see in a chemical reaction. So maybe you'd make chemical B, in a elementary step, and then maybe B is in another step below it, and it gets used up. That would be an intermediate. So it gets canceled out if you try to add everything up and make a overall balanced chemical equation. And not only that, you never see it in the chemical reaction. If you were observing this reaction occurring with all its steps, you would never see an intermediate. Because of that, we do not like to place it ever into a rate law, because rate laws are designed to be a tool for us to be able to manipulate the speeds of reactions. So if we never be able to, if we can't observe it, if we can't add it or subtract it, we can't really manipulate it. So we're going to always try to keep intermediates out of our rate laws, and we'll show you how to do that in a couple more slides here. Okay, so this would be a typical question that would deal with a rate mechanism. So let's see what we got here. We have a rate law that's already been given to us. It doesn't state how that rate law had been determined. That's not important. It's already also been told to us that it happens in 2 steps, this reaction. So N2O, I'm looking at step 1 here. N2O goes to N2 plus O, the atom O. And then in step 2, N2O combines with O to make N2 plus O2. Let's look at some, this nowhere in here, well actually it does. It says write the equation for the overall. So to write the overall reaction, we would just take all the reactants, put it on the reactant side. All the products, put it on the product side, combining step 1 and step 2. If there's something identical on both sides, we can cancel that. So let's just write this completely out right now. N2O is a reactant. I have another N2O as a reactant. I have an O as a reactant. And I have an N2, another N2, an O, and an O2. I think we could cross those out, and then we could combine those two. So I'm going to write that as the only reactants. That. So that's the overall balanced chemical equation. And then if we were able to cancel something out, very likely it's an intermediate. We'll also figure out there's something called a catalyst. We have another section for catalysts. But if you make a product in an earlier step, and then use that product up as a reactant in a step below it, that's an intermediate. So you never get to see this O ever. It gets made and then it gets used up. So that's an intermediate. What else were we told to do? So that we answered that part. And then let's go up here just a little bit. So it says, what can you say about the relative rates of step 1 and step 2? So the rate law, again, that was already determined for us, has to reflect the slowest step. And I had mentioned in a earlier unit that the coefficients in the balanced chemical equation do not match up with the order of reaction. But today, in the elementary steps, the slowest elementary step matches up with the chemicals and the coefficients in the rate law. So we have N2O. So do we have a step that has N2O and only N2O? We do. So we like right now step 1 as the rate determining step, the slowest step. And then what is the power order of reaction for that rate law? It's a 1. And what's the coefficient in the rate determining step? The slowest step, 1. So step 1 is our slow step, we could call it. We could call it the rate determining step. Either of those would be correct. Okay, another question. We have now a mechanism. Here's our mechanism. Now, this isn't really a question because all the answers are given here, but I definitely want to approach this because this is going to be a little bit unique here. It's already been told to us that that's the slow step. So, what you should be able to do is write a rate law using that slow step. So, rate law constant that's always going to be there. We have a reactant N2O2, and its coefficient is a 1, so it's a 1. And then we have another reactant O2, and it has a 1. So there's our rate law. But we have a problem with this rate law. And the problem with the rate law is that N2O2 is produced in step 1 and then reacted in step 2. That means that that chemical is an intermediate. And intermediates cannot show up in the rate law. So it looks like we have a problem here. You can't just go, oh, you know what, let me just erase that. That doesn't work. You can't do that. So we have to come up with a method that we could somehow still have a rate law that works for us, but doesn't have an intermediate. And with luck here, we were given a special type of reaction. This reaction is an equilibrium reaction. It's a double arrow. Think of it as that. So what does that mean? Wherever we have this, we could put that. So wherever we have the N2O2, we could put NO. But coefficient of 2 would be a power of 2. So that is a mathematical means of manipulating our rate law so we can actually use it. Now, why is this useful? Because I can manipulate O2. It's a reactant. So I could add more O2 if I wanted to. I could take O2 out if I wanted to. And then also NO is another reactant, and I could manipulate that, and that would have an impact on rate. So that's going to be you can only do that if you have a double arrow. Let's practice one of those. So determine the rate law. So our first idea would be to write a rate law with that slow step. So rate equals K times O3 to the first and O to the first. So those are our two reactants in the slow step, and the coefficients of 1 would be powers of 1. But we have a problem with that. And the problem is that atomic oxygen there is a intermediate. So can't use it. So are we able to substitute? Yes. And this substitution is going to look a little strange. Actually, it's going to look a lot of strange. So looking up at this step 1, we have this idea. Think of it as that. Now, remember that when we have these balanced chemical equations and we have these pluses, somehow they don't become pluses when we go into a rate law, they become multiplications. So using that same mathematical idea, we don't ever have subtractions. We don't ever have subtractions in chemical reactions, but if we did have a subtraction, instead of being a multiplication, I guess that would have to be a division. Think of like like, well, I'll get there in a second. So we have this oxygen that we don't want in there. Do we have anything that we could substitute in? Yeah, let's manipulate this mathematically. We have that. Okay, so what are the coefficients here? We have a 1 and we have a -1. Okay, so our rate would be K O3. We had that before. And then where we had O, we would have to put those two things in with their coefficients. So there's my O3 to the first, and there is my O2 to the negative first. And what is negative first really? It's really divided by. And then O3 times O3 would be O3 squared. That's going to be very strange looking compared to many of our other rate laws. By the way, either of these two, this one's not simplified, but it's just as good. It's just as good. And here would be another type of question you could get. I think this is our last question we're going to do today. Is we have some information here provided. So we have an overall balanced chemical equation. We also have that this is third order in context to nitrogen monoxide. So someone proposed a couple different, well, 3 different mechanisms here, and we're going to take a look, are these 3 possible? So let's take a look, do these mechanisms match up with the balanced chemical equation? NO, 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 that's 3 NOs, making N2 and O2, making N2O and NO2. So that looks like that works. So in terms of balancing, that mechanism looks pretty good. So we're not going to eliminate that yet. Let's see if we can. So the mechanisms 2 and 3 actually have multiple steps. So that would cross out. What would be left with? We'd be left with 3 NOs. 3 NOs. We'd be left with N2O. Okay. And NO2. Okay. So that looks like that matches up with the balanced chemical equation. Okay. This one has a rate determining step. So that means that the rate law should match up with that. So the rate would equal K, NO, and remember the coefficients in the rate determining step have to match the power, the order of reaction. So that looks like good, except it's supposed to be third order, and I have second order. So I don't like, for that reason, rate mechanism number 2 here. So let's look at rate mechanism number 3. So let's cancel those. Let's add those up. So 2 NOs plus an NO make 3 NOs. Okay. N2O as a product. Nice. And NO2 as a product. Okay, so as far as balancing chemical equations are concerned, this looks good. Let's just see if it matches up with the order of reaction. So we're going to use the rate determining step. And we do have an issue here. Remember that we were able to cancel N2O2. So that's an intermediate. That means wherever we had N2O2, we're going to now substitute 2 NOs because they're equal. So the rate determining step would have been, the rate law from the rate determining step would have been that. But we're going to substitute that in there because of that. And to simplify that, NO to the second times NO to the first is NO to the third. Third order, third order. So that looks, we have two of these that we really like. Well, I'm only allowed to get one answer. There's only one right answer. Well, it looks like there's two right answers. No, there is one right answer. So which one is most likely to occur? Well, let's revisit these. So for this to happen, the first mechanism here, you would need NO to collide with NO to collide with NO perfectly, right orientation, all at the same time. That is termolecular. Probably not likely to occur. Could it happen? Yes. Is it likely to occur? No. What's going on with this one? Rate determining step. We need two items to run into each other. So that is bimolecular. And bimolecular is going to be a lot more common than termolecular. So even though we like 1 and 3, we like 3 a lot more than we like 1. So that is definitely a AP style question because there was a lot of things involved there before we were able to get a right answer. The most correct right answer. Okay, that's it for today.